Okay, so if you think about the can crush demo that you just saw, at the end, clearly something provided a lot of force to crush the can. And that's atmospheric pressure. I'm sure you've heard that answer before. You've probably seen a can crush demo before. But it's interesting to think about the source of atmospheric pressure. And so we live on the surface of a planet and we live in an atmosphere. We're surrounded by air. We don't think about it a lot because it's transparent. We can't see it. We move our hands and it gets out of our way. We don't really feel it. But we would certainly feel it if it weren't there. If a human is removed from the surface of the Earth into the vacuum of space, very, very bad things happen when that atmospheric pressure is suddenly no longer there. We evolved in the atmospheric pressure, and so we need to have it in order to survive, not just for breathing, but just for our general health as well. So where does the atmospheric pressure come from? Well, we live on the surface of a planet, as I said, and the atmosphere actually has a mass, right? So we've got about a 50-kilometer high column of atmosphere above us. And if we take the surface area of the Earth, that's about 5 times 10 to the 14th square meters, and we take the mass of the atmosphere, which is about 5 times 10 to the 18th kilograms, we can see that that gives us a mass of, or sorry, a mass per square meter of 10,000 kilograms per square meter. Okay, and those units may not sound very familiar to you, but you may have heard of the pressure in pounds per square inch. And if you run the math, it's an interesting exercise in dimensional analysis and unit conversion to run the math on that, and you find out that that works out to be about 14.7 pounds per square inch, which is, of course, the value for atmospheric pressure that you're probably used to seeing. This is atmospheric pressure at sea level. Okay, and that's relevant because if you go up in the mountains, the atmospheric pressure actually goes down. At the top of Mount Everest, for example, you can see here on this graph, the atmospheric pressure is less than zero point 0.4. It's about a third of what you would feel at sea level. So we consider 1 atmosphere or 1 ATM to be the normal pressure at sea level, and then as you go up, Denver's a mile high, and you see that it's gone down by almost zero point 0.2 atmosphere, so it's only about 80% of what we feel. La Paz, Bolivia is even higher, almost twice as high as Denver, and so we've gone down to just about 63% of what you would feel, or 65% of what you would feel at sea level, and then at the top of Mount Everest, you're getting crazy, and this is why, climbing Mount Everest without oxygen to the summit is kind of crazy, because by the time you get up there, there's no air up there. Okay? There's very, very little air, and of course, oxygen's only a fraction of the air that we breathe, so the oxygen level has gone down proportionally, and you're only getting 30% or 35% of the normal oxygen you would get at sea level. So most climbers that go up Everest use oxygen. They bring oxygen up with them, and unfortunately, they leave the bottles behind. But that's a different story. So this is where the atmospheric pressure comes from, and the value of the atmospheric pressure depends on how much of the atmosphere is above you. Okay, so let's talk for a minute about how we would measure that pressure. What kind of device could you carry with you that would allow you to measure these changes in pressure at the different altitudes that we just talked about? That kind of device is called a barometer. It's actually a specific kind of manometer, and what we have is you've got the atmospheric pressure pressing down on this pool of mercury here, and so if we assume we're at sea level, then the pressure will be 1 atmosphere. Okay, and what we're going to see is that when we press down, if this is mercury at atmosphere, if we have a tube, so this is a sealed inverted tube that's evacuated, so all the air has been taken out of it, and if we put that open end of that tube into the pool of mercury, what happens is now the atmospheric pressure pushes down on the mercury, and the mercury rises up in the tube until the mass, the weight, the force of the mercury pressing down on the surface is the same as the atmospheric pressure pressing down on the surface. Basically, you had an imbalanced force, so that means something's going to move until the forces are balanced again. That's just basic physics. And so what happens is the mercury rises up in the column until the weight of the mercury column balances the atmospheric pressure. Okay, and so our 1 atmosphere here is going to equal, we'll find 760 millimeters of mercury. And so one of the more common units that you'll see for pressure is millimeters of mercury. So you need to know this. Unit conversion. And 1 millimeter of mercury is equal to 1 torr. So there was a Italian scientist named Torricelli, and his name became a abbreviated version of his name became shorthand for this 1 millimeter of mercury. Now, one thing that I should have mentioned before now is that atmospheric pressure is a pressure, and pressure is equal to force divided by area. Okay, and so that's just a basic definition of the physics quantities. If you study physics and you talk about pressure, you are going to learn about force per unit area. The other unit of measure that we would use for pressure is the physics unit, which is the Pascal. And we don't see actual pascals very often, but you might. What's more often is that you see kilopascals, because a pascal is actually a very small unit of force. And so the one other conversion you need to know is that 1 atmosphere equals 101.3 kilopascals. Pascal is PA, so kPa. So you may see pressure written in any of these units: atmospheres, millimeters of mercury, torr, or kilopascals. And you need to be able to do the appropriate unit conversions between any of those. Okay, so we can use that same technology, basically very simple, with a column of mercury to measure pressure in all sorts of different ways. And so this is the idea behind a mercury manometer. So changes in the height of a column of mercury are going to reflect changes in pressure. And so there's kind of 2 ways to apply this. You can use a mercury manometer that has a closed end. And so if we've got vacuum in this part of the tube, just like we did in the previous example. And so if we connect that to an evacuated flask, the difference in height between the 2 sides of the column of mercury is going to be 0, right? So the mercury is in this U bend, so you actually have your essentially connecting this volume and this volume, and the forces on the 2 different sides are going to cause changes in the height of the column of the mercury. And so if we have this evacuated and this evacuated, it's going to be 0. And now if we were to open this and fill this with gas, now that gas is going to press down on this side of the column of mercury, and the column, the change in the height here is going to reflect the pressure. So this is called absolute pressure. And so we might measure this as pressure absolute in this case. And so that is going to be equal to the height of the column of mercury in millimeters in millimeters of mercury, right? So if it went up 100 millimeters, then that would be 100 millimeters of mercury, and we could convert that to atmospheres by dividing by the appropriate conversion factor, multiplying by the appropriate conversion factor. This is one way to measure it, and that's how you measure absolute pressure. What is more often the case with these sorts of things is that you actually use an open end, and you use the pressure of atmosphere on the open end as a measure of the relative pressure inside your gauge, because evacuating things is expensive. And so now when you do it this way, what happens is you're actually measuring the relative pressure inside there. So instead of absolute, you measure the pressure relative. And so now the change in the pressure is equal to the change in the height of the mercury column. So you're always referencing atmospheric pressure. And if the pressure inside the volume that you've connected is less than atmospheric pressure, that means atmospheric pressure will press down harder here than the gas inside the bulb is pressing on this side, and the mercury will rise up on this side. So, of course, the sign of the change is now important. With absolute, you're measuring against vacuum, which is a pressure of 0, and so you can just say that the pressure is equal to the height of the column of mercury. Now we're talking about a change in pressure being reflected by a change in the height of a column of mercury, and so we need to take the sign into account. Okay, and of course, so that can go the other way as well. And so just to do a quick example of the unit conversions, if we had that delta P equaled 100 millimeters of mercury, we could convert that to atmospheres by dividing by 760 millimeters of mercury per atmosphere. Atmospheres on the bottom, that goes up to the top, and this would equal 0.131 atmospheres. After, of course, you can cancel out the millimeters of mercury here and here. Okay, so we're just going to finish up here by talking about the properties of gases macroscopically. And in the next video in this series, we'll get into the microscopic picture. But we're going to start to connect those now. So gases are highly compressible. Okay, so what this means is that if they occupy the full volume of a container, right, they're made up of little particles that are flying around, and they'll fill up any space you put them in. But if you change the size of the container, if you press down on a gas, the gas responds. If you compress a gas, its volume decreases. If you decrease the pressure surrounding a sample of gas, it will spontaneously increase its volume to fill the available space. Okay? Gases also always form homogeneous mixtures with other gases. Okay, so we know that if we just take two different gases and we combine them in the same chamber, after a short amount of time, they will be completely mixed. All right, so this is one of the reasons why we know that particles that make up gases are always moving around, as they just spontaneously mix themselves up. And so the molecular picture that's evolving, gases have very low densities, right? The only way that this can really work is if gases don't take up all the space in a container, right? Gas molecules only account for about 0.1% of the actual volume occupied by the gas. That means the space taken up by the molecules of the gas is very small, and most of what is in a sample of quote-unquote gas is actually empty space. And this is very different from the case with solids and liquids. When you have a solid or a liquid, the molecules, atoms, ions, whatever's are making it up are packed together very densely, so there's almost no space between them. And that's why solids and liquids are considered to be incompressible. You can press on them as hard as you want, and their volume just won't change very much. Okay? Whereas gas, even a small change in pressure will cause a response in the volume. That's because gas has this empty space that makes up most of the sample that the molecules can move in and out of, until, of course, the pressure gets very, very high, and then you get to the point where you're actually condensing it, right? You can force a gas to become a liquid if you push on it hard enough under most circumstances. All right, that's more of a topic for an advanced physical chemistry class in college, but the general idea is the same. All right, so that's the end of this video. The next video we'll start to get into the empirical gas laws. You do have a discussion assignment that you should go to now and finish up.